So I'm going to be talking about something called the fast inverse square root, which is sort of like a famous algorithm, weird kind of thing that showed up in the Quake source code. And then I'll also be talking a little bit about just like how computers think about floating point numbers, like decimal numbers, where the name float comes from. Just as a quick like mental note, how many people have taken CS357? Because the first maybe like third of the presentation will be a decent review of 357. Okay. Well, anyway, yeah, I'll go over. So usually when we talk about like numbers, we represent them using bases, right? I mean, like that's just what we've been doing for a long time. For example, like if you wanted to convert 425.91, like if you want to break that down in base 10, what that actually means is just 4 times 10 squared plus 2 times 10 to the 1 plus, 5 times 10 to the 0. And then once you get past the decimal point, the powers of 10 start going negative. So it's plus 9 times 10 to the negative 1 plus 1 times 10 to the negative 2. You can do this in any base, right? Like there's no reason we have to do that sort of concept in just base 10. You could also be doing this in base 2. So if you're going to represent, 11.25 in binary, that's how you'd write it. Because you've got 1 times 2 to the 3 plus 0 times 2 squared plus 1 times 2 plus 1 times 2 to the 0. And then once you get past that decimal point, you're going to switch to negative exponents. So in a computer, though, we have some downsides if we wanted to represent our numbers using this approach. Usually this is called like a fixed point or a decimal representation of a number. So say we had just 32 bits to represent a number, because that's usually like the size of an int that you work with in a computer. That's what we're going to represent our decimals in as well. We have a few different options. One, we could do 16 bits for the interior portion. So we decide that the first 16 bits are going to be positive powers of 10, and the next 16 bits are going to be negative powers of 10. If we do this, we can represent numbers as large as 2 to the 16, 2 to the 16 minus 1. And our precision is about 1.5 times 10 to the negative 5, right? 2 to the negative 16, 15, something along those lines. So we have a much smaller range at the top using 32 bits than we did if we had like an integer. But now we can represent fractions. The other thing we could do if we wanted to represent larger values is use 24 bits for the integer portion and then 8 for the decimal. In this scenario, you can go to a much larger number, but then we can only represent numbers down to like about 0.004. If you wanted to represent something finer than that, you'd have to round. Like you wouldn't be able to. So none of these are really great because one, we're either limiting how big in magnitude our number can get, or we're limiting how like precise we can get in the like decimal portion of the number. Floating point representations are very similar to scientific notation. So like when you write down the number 37.56, if you wanted to write that in scientific notation, you'd move it so that there's just only one digit after the decimal point, 3.756, and then you'd add a 10 to the 1 to like shift it back to where it's supposed to be. We can do the same thing in binary, right? If you have a number like this one, you could just shift this over. You could shift over the decimal point and then multiply it by 2 cubed to move it back to where it's supposed to be. One of the nice things about binary numbers, though, is that the first number is always going to be 1. If it's not 1, then it's a 0, but then that doesn't count as part of the number. So we kind of abuse that when we're storing things. We just get an extra bit of storage if we were going to store something like this. And this is sort of how we represent floating point numbers. We store some sort of like plus or minus q, and then times 2 to the m. M is the exponent, and q is the significand. But usually when we're talking about the significand, because the first number of that is always going to be 1, we only really care about the fractional bit, which we call the fraction or the mantissa. This is where the name floating point comes from. The actual like point can float between like where it is. And then we call them doubles because doubles are just twice as large as floats. I don't know who named those. But like if you're going to take away one thing, just like historical fact, like that's where the name float comes from. Decimal point floats. It's not fixed, as in like a fixed point representation. So we can represent a lot larger numbers, but our precision is kind of weird. So for example, say we chose to restrict our exponent to be between -4 and 4, and then we give ourselves 2 bits for the fraction of the mantissa. That's going to give us 6 total bits of representation. And then, like, what are the smallest and largest values in magnitude that we can represent with that? And just for simplicity, even though 4 bits gives you a range of 4 bits for the exponent gives you a range of 15 values, I've just shrunk it to -4 and 4 because I don't want to deal with like one side being +4 and one side being like -3 or something like that. Anyway, this is what that looks like if we were going to represent it. We have 1 bit, 2 bit, and then m, which can range from -4 to 4. And so the smallest value we can get is 0.00 or 0.0625, like in magnitude. And the largest value we can get in magnitude is 28, which is we set all the bits to 1 and then set the exponent to 4. So if you wanted to do a fixed point representation with only 6 bits, you'd be sort of left in a weird spot where, like, if you did 3 bits for the, like, after the decimal point, you could go all the way up to 8. And then if you did 3 bits for past the decimal point, you could only get about, I think, like 0.0125. Yeah, 0.0125 or 0.125. So using a floating point representation, because we let the float sort of vary, just with 6 bits, we can represent way larger numbers than we could with a fixed point representation. And we can also get more precise. But you can't really get precise between numbers, if that makes sense. So, like, for example, how would you represent 27 in a scheme like this? And the problem is you can't. You either have to choose 24 or 28 to represent 27, because there's no way to, like, manipulate these bits in this exponent to get to the value 27. What you choose as your approximation kind of depends. Usually in, like, scientific computation where, like, rounding stuff matters, you'll actually go with 24, even though it's further away from 27. But that's just because we tend to round down. But that's not ideal, right? So that's where IEEE 754 comes in. IEEE 754 is still doesn't really solve this problem, but it gets significantly better. This was thought up by, I don't know when 754 came to be, but a long time ago by really smart people that met in a room and, like, sort of concocted up a system. And the idea is that there's 1 sign bit, which is going to be, like, whether your number is positive or negative. There's 8 bits of the exponent. So that lets us represent 255 values, right? 2 to the 255 in the exponent. And then we get 23 fraction bits, which lets us get very, very precise. Like, you know, you can get a very small value. I think it's like 10 to the -14 or something like that. Okay, so yeah, just like I talked about, one special thing we do with the exponent is it represents a range from 0 to 255. We shift now in the exponent, the one that's, like, encoded in the bits, by 127, so that now we can represent negative exponents as well. So in that scenario, the largest exponent is 127, the smallest is 126, and then we reserve the exponents 0 and 255 for special cases. And then the last 23 bits are the mantissa or the fractional bit. I'm going to use those, like, interchangeably. So for the special cases, if you want to represent 0, because if you go back to the slide, it's not really clear what 0 should be, right? Like, we always start with a 1, so how do you represent 0? If you want to represent 0, you just set everything to 0. The one downside of this, which you'll see in languages that don't do a great job of, like, type safety with floating points, is that because the sign bit we don't really care about by the definition of 0, there's a concept of a positive 0 and a negative 0. And depending on how your language is implemented, if you compare those two things, they might not be equal, even though they represent the same number. So that gets messy. It gets even messier though. Infinity, if a number is, like, outside the range we want to represent, which, that might happen from, like, a computation. One of the nice things about IE 754 is that if you wanted to do, like, math in integers and you got something larger than 2 to the 32, then you would just, like, it's undefined behavior. Like, it's not clear what happens. It depends on the language specification, the compiler, and sometimes the hardware. In IEEE 754, we say if you get a value outside of that range, then we just call that infinity. So to represent infinity, you make the exponent 255, or, all ones, and then you set all the mantissa bits to 0. And then positive infinity is sign bit set to 1, negative infinity is sign bit set to 0, or other way around, sorry. No, the way I said it. Sign bit 1 is positive, sign bit 0 is negative. Sign bit 0 is positive, sign bit 1 is negative. You don't have to worry about that. That's not going to show up. Well, I mean, positive and negative infinity will show up, but you're not going to get, like, it won't show up randomly. You'll usually see it. And then there's also sort of same thing with integers and like longs and things like that. If you do something like divide by 0 or take the square root of a negative number, it's again up to the language spec, up to the compiler, up to whatever, like what actually happens. Maybe the hardware will throw a fault. Maybe the like compiler will throw a runtime error. Maybe the compiler will catch that because it's type safe and it'll throw a compile time error. But with floating point numbers, we specify a value, nan, or not a number. And the way we do not a number is we set all ones to the exponent, but we make the mantissa not 0. This has another major downside in that what we set the mantissa to is not specified. So again, if you've got a language with poor type safety, you might get nan, like you two things that are nan, and they won't be equal to each other because they have different mantissa bits if the language is not like sort of keeping that in mind in the background. So floating point numbers get kind of cursed. You can do a lot of really weird things with them. And rounding is a very important consideration that we'll probably not talk about, but you know, like it matters how you round things because you want to do floating point comparisons, things like that. And you know, based off of what I've described here, if you have two floating point numbers, even though they look the same, there might be like 1 bit change in the mantissa or something. And so you have to like specify like what tolerance of error do I have and comparing them, things like that. If you want to learn about that, I recommend taking CS357. But realistically, I didn't really like CS357 as a class, so just watch the 2 lectures that are associated with floating points and you can ignore everything else. But you should be very careful with them because there's a lot of gotchas, there's a lot of just weird things that happen when you do math with them. But that's not what we care about. What we really care about is how can we abuse this representation to just do things for us. So for example, what if you took the bits in a floating point number and then you pretended that it's an integer? Or what if you did the opposite? You took a number, like just a binary number, and you pretended that was a float. Some weird things happen that we can sort of take advantage of. But before I talk about those, does anybody have any questions about like fixed point representations, floating point representations? One slide that's not in here, but I was thinking about just like on the way here, is that just sort of just like sort of by the nature of like this rounding problem that we have, where like how do you represent 27? Is it 28 or 24? There's no like gap between numbers in a floating point representation. The gap varies as you go along like the curve. I think you can like plot I think it follows like a quadratic function or something like that, but it's not clear like what that gap is. So like one number, like you might have the number 24 in a floating point system, and then you might have like 24.75, and you might jump up to 28. Like it's not clear what the gaps are supposed to be. It's not clear what those are supposed to look like. So one of the downsides of floating point representation is that although you get a larger representation, and at small values you can like represent things more precisely, sort of in between those, it's unclear. With 32 bits, you can get pretty precise, like up to like 3 or 4 decimal points. You're never gonna like see any issues with that. But for more than that, you know, things start to get messy. So in a lot of like applications where you care about your data being like consistent, you probably wouldn't want to use a floating point representation. So in like finance and things like that, they usually use a fixed point representation up to like 3 or 4 decimal points. So that's what they care about. Anyway, yeah. Any questions about just like fixed point numbers, floating point numbers? Cool. So I'm just gonna ignore the sign bit for now and for most of the presentation because it doesn't really matter. Like you just toss a -1 in through various like things that we talk about. Say you had a number with a positive sign bit, then the number that we see is right, like the number is 1 point, like 1 point f, 1 point in the mantissa, times 2 to the whatever is represented in binary minus 127. If we took that back and we reinterpreted that as an integer, we get, because the mantissa is at the bottom, right? So that would be like added on. And then the exponent is, you know, 23 bits up. So we get c times 2 to the 23 plus f, right? Like we've taken a float and when you like treat that literally as an integer, you sort of get this value. Going the other way around is a little bit messier because you have to do like bits, like bitwise comparisons, like masks and stuff. So I'll leave that to you. We don't really care about it, but you can go the other way around. Like there's nothing stopping you. So we're going to take the fact that we could treat a float as an integer, and it sort of does math for us. Like it, you know, it computes 2 to the 23 times c plus f for us. And we're going to see how much nonsense we can make with that. So let's take the logarithm of our floating point representation, right? We have, so if we just like call f and c like variables for the f is the mantissa or the fraction bit, c is the exponent. If we take this is what we get, right? 1 plus f over 2 to the 23 times 2 to the c minus 127. This is like just in the floating point representation. Let's take the log of this, sort of thinking of them as distinct ideas. You end up getting this sort of messy thing. You get log 2 of 1 plus f over 2 to the 23 plus c minus 127. That makes sense, right? People are familiar with log rules. And in this example, f is like the number shifted up all the way by 2 to the 23. Because in the bits, it's off a little bit. And then for most things, you can approximate like log of 1 plus x is around log of x. Log grows so slowly that like doesn't really matter. And just to be safe, we can add a correction factor to make our, like you could tune a mu to make that approximation even like tighter. So the log now becomes f over 2 to the 23 plus mu plus c minus 127. And for no reason that's apparent yet, we're just gonna like pull that 1 out of 1 over 2 to the 23 out. We get f plus c times 2 to the 23 plus mu minus 127. Does anybody notice something about this? There's something really suspicious about what we get. And that's that our logarithm is basically some constant times f plus c times 2 to the 23 plus some other constant. It's a linear transformation of that integer representation. So what does that let us do? Essentially, if you've got a float and you want to find its log, you could just reinterpret it as an integer and then do that linear transform. And so basically for free, because we've done no division, we've done no computation, we've just reinterpreted bits and like done a multiplication and like an addition or a subtraction, we get the log of a number. So how'd you go back from log, back to the regular number? You would just reinterpret it. You would undo the linear transformation and then you'd reinterpret it as a float. So this gives us all of the log properties, which are quite nice for free, essentially, because we can convert a number to its log also basically for free. So the most important one, the one that we're gonna abuse for fun and profit, is that if you've got k times log x, that's the same thing as log of x to the k. So, x to the 1/2, if you want to take the square root of a number, that's the same thing as 2 to the 1/2 times log 2 of the float. And that's just, the integer representation transformed ever so slightly. So the question though is like, how do we actually find those constants k1 and k2? And we're still taking like an x, like 2 to the 1/2 is not easy. Like 2 to the 1/2 times something is not necessarily fast to compute. Kind of is, but it's still kind of messy, right? Like, how do we actually do this computation? And before we talk about that, let's just take a detour into the inverse square root, because that's sort of the historical motivation for what we're talking about. So Quake has this algorithm that sort of appeared on the internet, I think in like the 70s or 80s or something like that, that no one really knows, no one really knew at the time what was going on. I mean, they did because they wrote it. But when this appeared on the internet, people were very confused about like what in the world is going on here. This is an algorithm that taking a float does some magic. You can notice there's no divisions. There's no divisions. Divisions are extremely slow to do in a computer. And somehow it computes the inverse square root, 1 over square root of the number that's passed in. So there's a couple of weird things going on here. I found it really funny, for example, how they've got like a variable for 3/2, but like what? But anyway, something weird's going on here. We're going to talk about what is this doing? How would you maybe write one of these yourself for a function of your choosing? And before we do that, let's modernize this a little bit, because Sam's not here, so I can sort of talk down on game developers. They're doing some kind of cursed stuff, like even ignoring what's already cursed. Like this line here. What this is basically doing is this is reinterpreting the floating point number as a long. That's undefined. Like the way they're doing this undefined behavior, like don't do that. Let's rewrite this in C++, and it's still kind of cursed, but it's a little bit less like the compiler won't like you for what you're doing. And specifically, we're just using standard bitcast to convert these things. So what's going on here? We're taking some number, some magic constant that appeared out of nowhere. We're subtracting our number, like the float that we've passed in, casted to an integer, and then shifted over by one. Sort of maybe reminiscent of like a linear transformation, right? Like we're taking the log, maybe, and then we do some math with it that's also not super clear. So let's start with this. This is pretty straightforward. This is what I was talking about, is we're taking the number and we're reinterpreting it as a like long. So this is in C, this is in C++. I'd like to imagine the C++ is a little bit more readable here, where it like literally says bitcast, it says the type, like it's like a function. This is undefined behavior because the specification doesn't like specify what you're supposed to do in this scenario. The compiler could like send out an email if it wanted to or something like that. But most of the compilers will do sort of exactly what's written here, where you take the address of y, where y is like the number that's been passed in. You take that address, you cast it to a long pointer. So now instead of a pointer to a float, we're working with a pointer to a long, and then we dereference that pointer. But because they're the same pointer, we suddenly ended up with the long, interpreting those bits instead of like a float pointer. And this is defined behavior. This is completely legal C++ in C++20. Before C++20, you might have wanted to use like reinterpret cast or something. I don't know. This is nicer. It's a constant expression. So that's what that line is doing. It's pretty straightforward, but it's one of the more cursed parts of the code because it's like, I mean, you're never going to see that in real code ever. Then sort of the real crux of what's going on is this thing, is this magic constant. We have no idea where that came from, and subtracting like I shifted by one. So to sort of try and break this down, one thing we should remember is that -1/2 times like the log of y is going to be the log of 1 over square root of y, right? Like it's going to be the log of the inverse square root. So you can already maybe kind of see what's going on here. Well, we've got this I shifted by 1, right? That's I divided by 2. And then we're subtracting it. So that's negative, I divided by 2. So we haven't actually done the linear transformation that we talked about with like the logarithm, like converting to a log. But we've done part of it. We've done like the part that comes before the linear transformation. But that's the nice thing about linear transformations is they're linear and the order you do them doesn't matter. So yeah, let's call 1 over square root of y, capital Y, and let's substitute this into the bit representation. Like let's substitute the bit representation into this equation. We get 1 over 2 to the 23 fy plus f capital Y plus cy times 2 to the 23. This is just the bit representation of like, this is that linear transform that we talked about. That's just log of 1 over square root of y, right? Like these line up. And then this is just -1/2 log of y, right? So far, so good. And then if we solve for just like this, trying to get this on its own, we get some messy numbers, but they're not too bad. It's another, no, there's nothing else here. Essentially this thing, and hopefully you can verify this math for yourself, is just 3/2 times 2 to the 23, like some kind of messy constant, right? -1/2 of the bit representation. So going back to this part, the I shifted by 1 is clearly like this -1/2 of the bit representation. And then this constant is this thing, right? Like that's where that constant came from, is it's a representation of this thing. There's one problem with this though. That's that we left mu to be up to us, right? We said like, let's let there be like an error correction factor. You can sort of choose that like how you want. So how did the Quake authors come up with that mu? They didn't really. They just kind of guessed a number that was close enough and they took it. It works out well enough. Like the error that you get, no matter like what mu you choose, as long as it's somewhat reasonable, it's still going to be quite tiny with this approach. We'll talk about that a little bit. If you wanted to do something like this by yourself, ideally take the mu, do your algorithm, and then like vary mu and plot like what is the error that I'm getting if I do that. But yeah, there's the mu that they use here, like this constant they use here is actually not optimal. There's like people, once this was released and people sort of started to get their brain around what was going on, they did exactly this, is they implemented this, but they let that constant vary, and they found constants that were more optimal than the one they chose, but it's good enough for their purposes. Okay, then we cast back. This is pretty straightforward, I think, right? Like it's same idea as last time. We take I, which, you know, if you remember the code was a long, we take its pointer, take its address in memory, convert it to a float pointer. So now that address in memory, the C compiler thinks is pointing to a float, and then we dereference it. So now we've got a float, or in C++, you've got this. Please do this. Or if you wanted to write C and you wanted to do this and you didn't want to have undefined behavior, the way you're supposed to do this is by using memcopy. This is not, I mean, I don't really know. It's undefined behavior. The compiler can choose to do whatever it wants. There's some examples of like really wacky undefined behavior where, for example, you have like a function main and a function that's like never called, never used, that like prints something out. And you do undefined behavior in main, and when you run the program, it prints out whatever's in that function that you've never called, never used. When you have undefined behavior in your code, the compiler can choose to do whatever it wants. It could send an email, it could blow up your computer, or most of the time it'll just sort of do what you're asking in this case. But try not to use undefined behavior. If you wanted to do this in C, you use memcopy. If you wanted to do this in C++, we've got standard bitcast as of C++20, supported in all major compilers finally. But we're not done, right? We're quite close. We've got a decent amount of it, but we introduced like a good amount of error in our assumptions, like that mu that we chose, et cetera. Like we're still slightly off. And if you remember the code, there was some other sort of random math that it was doing that we haven't really discussed yet. So before we talk about that random math, this is sort of a hint of what's going on. We're going to take another detour into Newton's method, which hopefully you've all taken calc, but we're still going to review it. The goal of Newton's method is you want to find some value C such that for some given function f of C is 0. And the way we do this, the way that Newton sort of proposed that we do this, is we make a guess that is kind of close to C. Like we've got a value that we think is pretty good. And then we follow the tangent line until we get to it. So you build the tangent line out, which is going to be f of x0 plus the derivative of that f at like x0, where x0 is the initial guess you had. And then you try to solve for x1 in this equation. This is the tangent line. Solve for x1, you get this equation. When you repeat until you're happy. This is what that looks like, right? Is we make a guess for like where the 0 is. We go to the function at that point, go to the tangent line, follow it down, repeat until we're happy. Anyway, we want to find 1 over square root of x. So we want to minimize this error function where, given a y, this is going to be 0 if we've made the right guess, right? 1 over y squared minus x. If y is actually 1 over square root of x, this will be 0. It'll be x minus x. Everything will cancel out. So I didn't go through the process of taking the derivatives. They're not like particularly hard. But if you follow Newton's method, you take the derivatives and everything like that, you end up with this, like this is f of x, right? This is the derivative of that. Just move it out with the -2. And you end up with this 1/2 y0, where y0 is the initial guess you made, times 3 minus xy squared 0, where again y0 is that initial guess you made, and x is the number you started with. It's the number that you actually like want to take the square root of, inverse square root of. So this is that code again. This is what's going on here, right? They've distributed the 1/2, but it doesn't really matter. You've got 1.5 f minus the number times 0.5 times y squared. 1.5, like that 3 times 1/2 is 1.5 minus 0.5 times xy squared, right? Same thing. And then all that times y0, all that times y0, which is our initial guess. And then the original Quake code, I don't have it from here, and I don't want to go back like 30 slides. The original Quake code actually had a commented out thing that said like second iteration, but it was commented out. You can keep repeating this if you wanted to, but the Quake developers found that like just doing it once was good enough for whatever they needed. Right? Is that sort of demystified? It's a bunch of really weird code, but it all kind of makes sense when you think about it. And the nice thing about this is that you could do this for any function. Like the process we walked through is not like particularly complicated. The main goal of doing this is to avoid divisions. So there are some functions where you try and do this, and maybe you'll get to like a derivative where using Newton's method, you're forced to do a division, or maybe you get to something else where like just that bit casting will require you to do a division. Like maybe you can't just divide by 2, you have to divide by like if you want to take 1 over square root of, if you want to take the inverse cube root of something, you'd have to divide by 3 instead of divide by 2. So you couldn't bit shift by 1 anymore. So it kind of defeats the point of just like trying to save on a division, but it could still be useful in a lot of like cases. Anyway. Yeah, so that doesn't have any divisions. Yes. And log of the inverse square root is the floating point number shifted around, like transformed linearly, right? Like you reinterpret the number as an integer, then you shift it around linearly. So if we go back to this slide, basically, we're trying to find log of 1 over root y, just like we're doing it in one step instead of doing like whatever. Or like instead of doing the linear transformation for log and then multiplying it by a half, we're just like finding it in one go. And you get this essentially, right? Like this this is the original constant. What is that? Right. Oh, it's because we shift things over. This is the original constant that we're looking for. This is 2 to the 23 times 127 minus 0. But because we're taking the inverse square root, we just decide to like lump all the constants together, if that makes sense. Like taking 1/2 of the log is just taking 1/2 times the log, and the log itself is just a linear transformation. So we just lump that 1/2 or that negative 1/2 into it. Does that kind of make sense? And so just really derive the log. Like you have this like you have this expansion of like this is the logarithm. If you just want to take the log, like this is what you can do. Where f plus c times 2 to the 23 is that integer like recasting. We've just taken that step and also done the negative 1/2 at the same time. The negative 1/2 and the sorry. The negative 1/2 and the conversion back at the same time. Because to convert it back to a number, you'd have to undo the linear transformation. So we've done all of those steps at once by just like doing some algebra, where we're trying to solve for f big Y in its floating point representation, or in its integer representation. Does that make sense? Cool. Okay, cool. Yeah, there's no divisions in the inverse square root, so it's like fast. Quake uses this for the inverse square root, and the reason Quake, I've never actually played Quake. I don't know if anybody has, but Quake is like it's a shooter, right? It's like an arena shooter. Yeah. Okay. But either way, when you're doing 3D graphics, a really common operation is normalizing a vector. So the way you normalize a vector is you just take its magnitude and then you like divide by the square root of the magnitude. So dividing by the square root of something is a very common operation in game dev. They wanted something to make that as fast as possible. This is what they came up with. And we can approximate a lot of functions using this method without using any divisions. It gets a little iffy depending on the function. You might still have to do divisions, but at the very least, that's on a later slide. But at the very least, you can approximate most things by either minimizing divisions or like minimizing complex log calculations. Yeah.
And so when you say you need compiler writers or software authors?
Software authors. Yeah, software authors. The compiler is unfortunately not smart enough to figure this out. Kind of. Because it's like, because you're doing an approximation, like you're going to get some error, and the compiler doesn't want to put in code that might be, like it doesn't want to convert your inverse square root into an inverse square root that is like 0.03 off sometimes, right? So this is something that if you were really like, you run a profile in your code, you're like, dang, we're dividing by the like the cubic root a lot, and like it's taking up 10% of our runtime. Like, here you go. I don't know when that'll happen in game dev. I mean, clearly it happens a lot. And specifically, I think there's a lot of code where you take logarithms. And if you run a profiler as a software engineer and you're like, hey, we're just computing the log on our data set is taking too long. We don't really care about exactly how detailed it is. One common example of this is if you want to like do data analysis or like something on a data set and it's got negative numbers, often you take the log of the entire data set to get rid of those negatives and then you undo it. But if you don't if you don't really care about how that log turns out, as long as like that error is consistent, then you could do, something like this. But unfortunately, we're not allowed to have fun like that anymore. Intel SSE, SSE, which is found on a computer, like basically any computer made after 1999, has the R square root SS instruction in it, which does the inverse square root. A little hard to read, but essentially at the top here, we've got the Quake square root, inverse square root that we talked about. And down here, we have the dumb square root implementation, and we just do 1 over square root of f. Compiler turns this into pretty optimized code, actually. Like if you read this, it's hard to read, but if you read this, it's pretty optimized, but it's still I don't know how many, 15 lines, everything included. The compiler for the inverse square root function just follows that R square root SS instruction, and that's going to be faster because it's implemented in the hardware. The actual approach that it uses is actually very similar to what Quake square root does, but they cheat sometimes. They do analysis on the number, and if it's a number that they already know, they do lookups in a log table. Otherwise, they do Quake square root algorithm. But either way, the hardware is just it's just faster. It's in the hardware. It's got a dedicated space for it to be run. So we're not allowed to have fun anymore. But you can still do a lot. It's just, inverse square root is such a common operation that it's built into modern hardware. Any game you play is probably calling inverse square roots every frame 20 times. But if you're going to take away anything, from this presentation, one, it's that floating points are kind of cursed. Two, it's that floating points are called floating points because the decimal point floats. I just think that's a cool trivia thing. And then three, if you're ever taking a log or you're doing some operation and you're realizing you're doing some math and you don't care about the speed, or you do care about the speed, but you don't care about exactly how precise it is, you're okay with a little bit of error, you can abuse the fact that a log is just a linear transformation away. So with that said, are there any questions? Cool. Okay. I'll still be here if people just want to ask questions. I know a lot about just floating point numbers because I was forced to take CS357. And then just the John von Neumann quote. Cool.
George, are there any other instructions that how to address certain operations that are common more efficient?
I mean, there's a square root instruction as well. That's just sort of an approximation, but it's not quite the same thing. There's a log operation that is exists in the hardware that is just a lookup table. It's just because 2 to the 64 only has 64 possible logs. So they just put all 64 in there. You do some casting, you do things like that. I think that's still slower though than if you don't care about the log. That's still slower than converting to an integer and doing linear transformation, because multiplications and additions are extremely fast. Looking up a table in memory is still pretty fast, but I don't know, off the top of my head, are there any other? I mean, so a really common one actually is a fused multiply and add. And it's just especially with machine learning, it's so common for you to do x times y plus b or whatever, that there's just a hardware instruction for that does that operation faster. It's just sort of this is sort of a fight between compiler engineers and computer engineers, where people start using things, so compiler engineers start looking into how to optimize them, and then computer engineers just put out a new instruction. That's well, what do you? I don't know. Yeah. Ooh, trigonometry. There's a Stanford graphics. It's from 2007 or something. There's a Stanford graphics web page that just talks about floating point hacks that, or just bit hacks that are common in graphics, because game developers are kind of insane and they really care about eking out every bit of performance. So there's just a lot of stuff with that. I was looking at that page and I feel I recall there's some insane way to calculate powers using a lookup table and bit shifts. So rather than doing if you wanted to cube something, there's just some it's approximate, but there's some bit twiddling you could do to get the cube of a number in integer, not necessarily a floating point number.
by just using a lookup table and doing some shifts. If you look up like Stanford bit hacks or something, it'll probably show up.